Good morning. I am Dr.L.Bharathi, Professor in AC Department, Sri Shanmukha College of Engineering and Technology, Sangagiri.
Today class, I would like to discuss about different types of rays which are traveling through optical fiber. Before we are going to discuss about different types of rays which are traveling through optical fiber, let us see the review of previous video. There we have studied the acceptance angle theta A and numerical aperture NA and importance of numerical aperture. These are all very important parameter in optical communications. So based on this concept, we will go and study about the different types of rays which are traveling through fiber. It is mainly classified into three types. One is axial ray, another one is meridional rays, third one is skew rays. As we know already, axial ray and meridional rays we have studied in videos 1 and 2. The diagram shown here how the lights are traveling through optical core. See, the axial ray which is traveling only through center axis of the core medium. This is called axial ray. Whereas meridional rays which is traveling along the core media through surface to surface and crossing the center axis of the core. This is called it as a meridional rays. Coming to that skew rays, which is shown in the second diagram, the definition of skew rays, it define the ray which will travel along the core media through surface to surface and not crossing the center axis of the core medium. So the skew rays front cross section is shown here, as well as meridional rays. The front cross section is also shown here. The meridional rays front cross section is just like a surface to surface crossing the center axis, whereas in the front section of cross section of fiber in skew rays, it is shown as the light travel from surface to surface just like a helical shape. These are the different types of rays which are traveling through optical fiber. Let us see the next slide. The skew rays, we can study detail about skew rays here. Optical ray which will travel along the core through surface to surface and not crossing the center axis of the core. It follows a helical path through the fiber which is shown in the diagram. Here optical fiber which consists of two medium. One is a cladding medium, that inner medium is a core medium which having refractive index n1, the cladding is having refractive index n2. Now the light is entered from air medium into interface of air and core medium. Then it's getting refracted into the surface of core medium. Then from there it's get refracted into the surface. Then it's getting slowly it's getting reflection from surface to surface, and it is traveling through fiber. So it is traveling like helical path. So called it is a skew rays. The same path it is showing in the fiber cross section area, the front cross section area. Let's see here, even the light is enter into the surface of core medium, is getting reflection here, and again getting reflection to another surface medium, then another surface medium, then it's getting, so like that it's getting multiple reflection from surface to surface and traveling through fiber but not crossing the center axis of the core medium. Let us consider one multiple reflections at an angle 2 gamma, which is denoted by 2 gamma, where gamma is an angle in between radius of the core and ray projection, nothing but gamma. For one reflection, the angle denoted by 2 gamma. So now from the fiber cross section ray traveling, it is representing the ray travel only from surface to surface, the to outer surface area of core media, where it never crossing the center axis. So called it is a skew rays. Then skew rays can be determined, and from there we can calculate what is the numerical aperture of skew rays. Let us see. in detail in the below diagram. Now, the optical light enters from air medium into interface of core and air medium at point A. From point A, the light is getting refracted into the another surface of core medium at point B. From there is getting from there it's getting internally reflection into the same medium. Likewise, it will be traveling through surface to surface and crossing the center axis, as we know already. Now, in this optical fiber, we consider the dotted line. See, the point A to T, it is one of the dotted line, which is nothing but upper surface of core media, which is parallel to the center axis. Then the bottom surface of the core media, okay, along the B point, okay, this is also parallel to the center axis of the core media. So with these three reference point line, we can calculate the numerical aperture of skew rays. Point A and B, the ray is refracted from top surface of core media into the bottom surface of core media. From there, it's getting reflected back to the same media, to the top surface of core medium. So here one multiple reflection taking place. So which is known as 2 gamma angle, 2 gamma angle, where gamma is nothing but, see here we have mentioned gamma angle in between ray, in between radius from the center axis of the core, radius from the center axis of the core, and ray projection from T point. Then again, also in the input side, we can find out gamma angle in between, the center axis of the core media and light projection area, and theta angle between the top surface, parallel line, and the ray projected AB. We can identify sin theta, here sin gamma, here cos pi. Based on these three parameters, we can calculate what is a numerical aperture of skew rays. Here, the reflection at point B at an angle pi may be given as cos gamma sin theta equal to cos pi. Let us consider here cos gamma sin theta is nothing but one of the incident angle, cos pi is one of the reflected angle, as per the statement of Snell's law. Okay, using the trigonometrical relationship, sin squared pi plus cos squared pi equal to 1. So now we can identify what is cos pi. Therefore, cos gamma sin theta equal to cos pi, which is equal to 1 minus sin squared pi whole power half. Now, this cos pi sin theta is nothing but multiple incident angle, cos, gamma, and sin theta. Now, we can calculate, sin pi is incident angle and critical angle. As we know already, sin pi c equal to n2 by n1, where cos gamma sin theta is less than or equal to cos pi c equal to 1 minus n2 square by n1 square whole power half. See here one point, a very important point here. The incident angle, cos gamma sin theta for skew rays is less than or equal to critical angle cos pi c, that is equal to 1 minus n2 square by n1 square whole power of. At this case, internal reflection is taking place. Whereas for meridional rays, we used to say sin theta I, theta I incident angle should be greater than critical angle. If that is the case, total internal reflection will be occur if it is a meridional rays. Whereas if it is a skew rays, that incident angle, cos gamma sin theta must be less than or equal to cos pi c. Automatically, total internal reflection will be occurred. But here side, this is a general meridional rays angle. Okay, then let us go for another one. By taking Snell's law at a point A, n0 sin theta A equal to n1 sin theta. Let us consider here at point A, the light enter from air medium to core medium. So when the light is enter from one medium to another medium, the Snell's law come into system. As per the law, we can write the expression n0 sin theta A equal to n1 sin theta, where the theta is nothing but refracted angle, theta is nothing but incident angle or acceptance angle for meridional rays. As per the concept, okay, even for skew rays we can determine, we can write the expression. Okay, now you take that Snell's law, we can take that skew rays law equation, you substitute in that meridional rays law. Therefore n0 instead of sin theta, we can bring out cos gamma sin theta as, that is equal to same n1 instead of sin theta, we can substitute cos pi c. So this expression representing, Snell's law for meridional rays, this expression representing, Snell's law for skew rays. Therefore sin theta as equal to n1 by n0 cos pi c by cos gamma, that's equal to n1 divided by n0 cos gamma 1 minus n2 square by n1 square whole power half, where cos pi c equal to 1 minus n2 square by n1 square whole power half. Therefore the acceptance angle for the skew rays, sin theta as, okay, cos gamma equal to numerical aperture, where sin theta as equal to numerical aperture divided by cos gamma, where theta as is nothing but acceptance angle for skew rays, where theta a is nothing but acceptance angle for meridional rays. Therefore theta as, therefore theta as equal to sine inverse of numerical aperture divided by cos gamma. This is a acceptance angle for skew rays, that S mean for skew rays here. Okay. Therefore, for meridional rays, cos gamma is equal to unity and acceptance angle for skew rays become equal to theta A, acceptance angle for meridional rays. Here, although theta A is the maximum conical half angle for the acceptance for meridional rays, it defines the minimum input angle for skew rays. This is a beautiful point mentioned here. But theta A is the maximum angle for meridional rays, whereas theta A here mentioned as a minimum angle for skew rays. That is a concept. Therefore, the skew ray tend to propagate only in the annular region near the outer surface of the core and do not fully utilize the core as a transmission medium. This increased light gathering ability may be significant for large numerical fiber. Now, large numerical aperture fiber. But for most communication design purpose, the expression given for meridional rays are considered adequate numerical aperture. So, numerical aperture is restricted, is limited, okay, for both meridional rays and skew rays. Let us go for the numerical aperture for meridional rays and skew rays. I have given one example to compare the numerical aperture of both rays. Let us see the problem 1. An optical fiber in air has a numerical aperture of 0.4. Compare the acceptance angle of meridional rays with that for skew rays with change direction by 100 degree at each reflections. It is very important here. 100 degree at each reflection. So that each reflection denoted by 2 gamma, total 100 degree, each gamma will be 50 degree. So based on that concept, we can go for the solution for the problem. The first one, for meridional rays, theta A equal to acceptance angle, theta A equal to numerical aperture of theta A equal to sine inverse of numerical aperture, that is equal to sine inverse of 0.4, that is equal to 23.6 degree. This is for meridional rays. Whereas skew rays, they change direction by 100 degree at each reflection. Therefore, gamma equal to 50 degree, as we know that. The acceptance angle for skew ray is theta as equal to sine inverse of numerical aperture by cos gamma, that is equal to 38.5 degree. See, the acceptance angle for meridional rays, acceptance angle for skew rays, I'm sure that based on the concept, the skew rays acceptance angle is very high than that meridional rays acceptance angle. If acceptance angle is greater in skew rays, of course, numerical aperture is also increases. That's a conclusion from meridional rays and skew rays. If acceptance angle increases, numerical aperture is also be increased. This is what theta A is less than theta AS. Therefore, numerical aperture for meridional rays is less than numerical aperture for skew rays. Okay, this is a very important phenomena, how numerical aperture for meridional rays and how numerical aperture for skew rays is calculated, and what is the importance for optical fiber. Next, we go for some assignment process. I have given here 4 assignment questions based on the previous videos. The first assignment is explain how is light traveling through optical fiber with neat sketch and equations. I think we may get answer from the first video once if you understand the concept. How is light traveling through optical fiber with neat sketch and equations? Then second question, how optical fiber is collecting maximum light from the source? Explain with the necessary diagram and the equations. I think if we go through that second video, we able to answer for these questions based on acceptance angle and numerical aperture, and with some diagram and the equations, we able to answer for these questions. Try to understand what is numerical aperture, what is acceptance angle, how to derive the expression, all those things. Then come to the third question. What is skew rays? Derive an expression for numerical aperture of skew rays. I think the third videos explain about these third questions. What is skew rays? Derive an expression for numerical aperture of skew rays. Good. Then fourth one, how can numerical aperture be increased when the light enters to the optical fiber? This is one of the very good questions. Maybe university questions or some other when you go for the interview and all, definitely they may put up questions. How can numerical aperture be increased when the light enters into the optical fiber? So this is very important. As we know already, based on the acceptance angle and based on the numerical aperture and based on the core and cladding difference, and that delta, relative refractive index difference, and n2 become their refractive index. By considering all those parameters, we able to answer for these questions. Okay, so now from these 3 video, almost we have studied about basic important parameter, basic concept, light rays and different types of fiber, different types of rays, and what is Snell's law for refraction, what is numerical aperture, what is acceptance angle, what is meridional rays, what is skew rays. All those things we have studied so far. Next, we are going for cylindrical optical fiber and how the cylindrical optical fiber is going to support for mode, number of modes. Okay, we will study about the cylindrical optical fiber and number of modes supported by the fiber in the next slide. Okay, so till that we studied a lot of basic things. Next we go for the another slide. So thank you.